This video will talk about encryption in a little bit more detail. First of all, I want to start with how successful encryption can be in both wartime. So for example, if you are trying to provide messages to your troops, you don't want the enemy to be able to know what you're saying, so you encrypt them. But on the other side, you want to be able to decrypt the messages of your opponent to be able to know what they're doing. The Enigma was a group of machines that worked together during World War II to decrypt the messages from the Germans. It was Alan Turing, a British scientist, and his team who broke the code, and their efforts is credited with cutting off several years from World War II. And if you look at this particular design here, you can see it has like Caesar ciphers with letters and rotating cylinders to be able to transpose numbers and letters as the encryption was, changed. And that was really the key. Is it was a changing encryption that was very difficult for the team to realize. So to understand encryption, we need to look at a couple of things. And one of them is binary operations. And binary, as you know, represents how the computer looks at things in zeros and ones. Because, a computer can only look at on and off electrical impulses. It doesn't have anything more sophisticated than that. And this is interpreted as binary code base 2. And there's several different operations that we are going to talk about, the AND, OR, and XOR. And the XOR is where we're going to head. But we're going to review all of these. So let's first talk about binary. How does it work? We operate in base 10. And base 2 is different from base 10 in the sense that 2 to the 0, 2 to the 1 is 2 to the first, 2 to the second is 4, 2 to the third is 2 times 2 times 2, which is 8, 2 to the fourth is 2 times 2 4 times, which is 16, 2 to the fifth is 32, and it's positional, okay? So everything is like, this is the first, this is 2 to the 0th, 2 to the first. So if we look at the number 23, we go to the furthest possible iteration we can get to when we get to 16, for example. So in that position, under the 16, 2 to the fourth, we put a 1. So 16 minus 23 is going to give us 7. So obviously 2 to the third isn't going to work. 2 squared, though, 2 to the second, is going to be able to work because 16 plus 4 is 20. 2 to the first is going to get a position because that's 22. And 2 to the 0th, 1 is going to work. So we're going to, our number then is read from right to left, 1, 1, 1, 0, 1. We could do this exercise again with the number, we can do it backwards, so we can say this particular example, we have 16. 16 and 8 is 24. 24 and 4 is 28. 28 and 0 is 28. 28 and 0 again is 28. The number is 28. And here is a website that you can go to be able to do this calculation from base 10 to base 23, base 2, if you so are inclined. So the reason we want to talk about this is because in encryption, we're comparing numbers, okay? We're comparing sets of numbers to be able to determine a message. And one of the operations in this binary operation is the AND. And in this particular example, we have a situation where we have one number. This number is actually the number 13 if you were to calculate it out. And we have another number, which this number is 8, 9. This is the number 9. And we compare, and we want to say, if both numbers have a 1, then the result is a 1. So here we go 1, nope, doesn't have a 1. Both aren't 1, 0, and 1. So our number reads back 1, 0, 0, 1, which 8, and the message turns out to be 9. Now, if we want to go to the OR operation, it's if 1 is in either or both, then it's a 1. So in this situation, we compare those same two numbers, and we get a different number. We see that we have 1, 1, 1, either or both, 0, up here's a 1, and here's a 1. So now our number is different. Now our number is 13, same as this one. So the or the and give us different results. Now the XOR, which is most important, is if a 1 is in one of the places, then it's a 1. But if 1 is in both, then it's a 0. So, and if a 0 and a 0 is a 0. So 1 is in both, so it's a 0. 1, 0, 0. 1 is in only one, so it's a 1, and it's a 0. So here, if we look at the number, we have a totally different number now that has come up with it, and we know this would be 0, this is 2, 4. We get the number 4 here. So it just gives you an example of how this particular works. All right, so why is this important? Because the XOR is the only reversible binary operation. We could go backwards to get those numbers. And it is the basis for single key encryption. Single key encryption means that there is one key that Bob sends Alice a message with a key, and Alice used that same key to decrypt what Bob says. It uses a substitution process. And so you can see it's not that super secure. In the terms cryptology, there's a few things we need to be able to know. These words. So key, it's the bits that are combined with the plain text to encrypt it. So I'll say it again. It's the bits that are combined with the plain text to encrypt it. And in some cases, this is a random number. In some cases, it's just some mathematical operation like we did. Plain text. It is the beginning, the unencrypted message. So we take this unencrypted message, we apply the key, and then we come up with a ciphertext, the encrypted text. And this process is an algorithm. So, for example, if we had something very simple, Bob goes to the store, and for every B, we change that letter. Our key says change all B's to C's and all, A's to B's. We just move it over one letter. Then the key applied to the plain text would come up with a very different answer. And that would be the algorithm. Move every letter over one. Clearly, that's not very secure. Symmetric encryption has two types. It's first it's the same key to encrypt and decrypt, but it can read either one bit at a time, which is called stream encryption, or it could block read, which is called block ciphering, which it reads a block at a time. So stream ciphering and block ciphering. One of the first standards that came up was something called Data Encryption Standard, DES, which looked at 64-bit blocks, of which 56 bits were the message and the key, the message that was changed by the key, and then the first 8 were things that had to deal with the actual key itself. It did a lot of different iterations. You can see it manipulated the encryption 16 times. It scrambled, it swapped, it transposed. It did quite a few things, but it wasn't that secure. And the reason it wasn't secure is because computers became faster, memory became larger, and we were able to go through those 64 bits with transposition and substitution very quickly to be able to come up with what was the message. So what they said is, we've got to increase the size of these blocks that are being deciphered, and that's where we came up with this advanced encryption standard. And it works with block ciphers that work on 128, 192, or 256 bits. And this is what is being currently used by the US government for symmetric keys. So AES and DES are both symmetric key encryptions. But one problem with symmetric key encryption is, how do you transmit that symmetric key? How do I tell Bob, I'm Alice, how do I tell Bob what my key is? I could send it in an email, but Eve might be listening. Google knows. So the answer was to come up with something called public-private key, or public key encryption, which is the same as asymmetrical encryption. And opposite of single key encryption, this uses one key, the public key, to encrypt the message, and one key, the private key, a different key to decrypt it. And only the holder of the private key can decrypt the message. And it's really focused on large prime numbers and factoring and numbers theory to be able to do this. So if we look at this particular example, the sender has some plain text. They encrypt it using the public key. It goes over as ciphertext, but the receiver has this private key that they use to be able to decipher it. Two different keys, public and private. Excuse me. So another type of privacy that's used quite often is something called pretty good privacy, because you can see that symmetric isn't that secure. Asymmetric is definitely more secure, but it requires more resources to be able to do these different keys to be able to do it. So pretty good privacy is something very commonly used in email. Gmail, for example, under Chrome, I give you CryptUp, which is an extension you can add to Chrome to be able to add pretty good privacy algorithm to your email. It uses both an asymmetric and symmetric method. Data is encrypted with a public key, but the key is encrypted with a private key. Each symmetric key is used only once, and it's called a session key. And I think that is an important component here, this idea of a symmetric key. It's only used once. An example of this is here is the message. We encrypt it. We get some random key. Here is the key. If you can look at it here, 16 characters. It encrypts the data, but also the key using RSA, in this case, encrypts the public key, and the message goes with the encrypted data through the public key and the encrypted public key using RSA private key. So how does somebody decrypt it then? The encrypted message comes, the encrypted public key, which needs to be decrypted. So you have to decrypt the key in order then to decrypt the message. This was created by Phil Zimmerman in 1993, made available on a free download. This poor guy went through quite a bit because it is difficult for government. Pretty good privacy is actually something that Snowden used when he downloaded all of the documents that he put on WikiLeaks. Okay, so some things to know about encryption, some warning signs of fraud. If they say it's unbreakable, that's not true. Nothing is unbreakable. If they say it's certified, nobody is certifying anything. And unless there's a lot of literature written about it, if it's not done by experienced people, don't think that it's going to be very secure. Okay. Digital signatures is another form of encryption. And this is a little different because it asks the question, how do you know if the person who you received this encrypted message from is the actual sender? And there's a term called non-repudiation, and I'm going to ask you about this on the exam because this is a term that is known within our industry of cybersecurity. Non-repudiation determines if the person that sent the message is the actual sender. Because a digital signature is not used to ensure the confidentiality of the message, but rather to guarantee who sent the message. And it simply reverses the asymmetrical encryption process. So let's see how this works. Okay, so here we go. We have John stamps his digital signature to the email by using his private key and then sends it to Mary. So here we go. John's private key, he emails it, goes through the internet. Mary gets it and uses John's public key to verify the signature. How is this different from asymmetrical? In asymmetrical, John sends the message using his public key, and then Mary uses her private key to read the message. So digital signature is reversed. It uses John's private key to verify who he is for his signature, and then Mary uses John's public key to verify that it's John. In both cases, it's John's private key John's public key. Okay. So I'll know the difference between digital signature versus asymmetric encryption. So, like I said, non-repudiation, digital signature, they simply reverse the asymmetrical process, meaning we send the private key over, Mary uses the public key to read it. And here it says the sender encrypts something with his private key, the recipient decrypts it with the sender's public key. This tells us that it must have been sent by the person purported to have sent this message. This is very important. This is one of the key components within encryption to understand. Hashing is another type of cryptographic algorithm, and some very key things. So for example, Windows has its own file, a SAM file, where it takes passwords and it stores them in that SAM file, and it's hashed. Hashing is one way. You don't decrypt something. It just creates a table value that when you log on, it compares what you log on with the value in this table that's already been hashed. And if the value doesn't match, then it knows that it's not the right password. So it's one way, you can't unhash it. It produces a fixed length output no matter what input is given. And the key is it should have fewer or no collisions, meaning that if you put two different things in, it's not going to come up with the same hash value. And the latest version is SHA-3. So here's an example. We input the word fox, we do the algorithm, and even though it's only 3 letters, we come up with this digest. And this is the word. Digest is the word for a hashing output. Digest. Fox. Here, the red fox jumps over the blue dog, put it through the function. Once again, we come up with the same fixed length digest. So you get the idea that this is the hashed value, comes up with the same length that, and this is determined by you. You've decided how long this can be, by the way. And it's in a table. And so then when you put the word, if you put the word bear in here, it says, I don't see anything when it goes to this hash function, because the hash function doesn't change. When it looks through it doesn't see anything that looks like bear. It says, oh, sorry, that's not the right password. It's not the right input, and it won't accept it. So that's an example of hashing. Rainbow tables are examples of what hackers use for hashing. So, for example, you can buy these rainbow tables, and they have all of these different iterations of passwords and things that you then can just match and see if they, you can use them to crack passwords, and that's what password crackers would use. Now, one thing you can do is you can hash with something called salt. And salt are random bits added to further secure it. Most often encountered with hashing to prevent rainbow table attacks. So, you saw before example, for example, you saw before AAA, and it came up with this hash thing. If you were to add a bit every four bits here, every 4 characters, you would totally change what this is. That adding those random bits is called salting. So for example, here is a password without salt, blah, blah, blah. Now we decide to add some kind of a salt here. Every so many characters, we add something. The message totally changes. So here we have a B, but it has a very different message. Password, and it's the word password, and then R $3 $RT. That's the salt. That's added, interspersed within this text. Okay, so you have a password and it's pass001, it's binary. Salt algorithm would insert bits periodically. So for example, here it's 0111100. Now it's 0111100. every fourth bit, it added a 1. So here's a 1 and here's a 1. So all of a sudden, it's a difference. So if you convert that text, you would get something totally different than pass 001. That's called salting. Stenography is just the art of hiding messages in pictures, videos, audios. So here is the Mona Lisa, and here is some Carpe Diem, a message hidden within it. It can be in videos, audio files, other digital artifacts. It's very interesting. So payload is the data to be covertly communicated. So in this particular example here, here's the payload. The carrier is the file. So in that particular example, the carrier is the signal, stream, or data file. So it would have been that JPEG, and the channel is a picture. Oh, sorry. So some examples of stenography over history is the Chinese wrapped notes in wax and swallowed them. That sounds very painful. The Greeks had their messengers shaved their heads and wrote a message on the head, then have his hair grow back. That sounds like it would take a long time, so you wouldn't want to do that in a pinch. And then Johannes Trittimus wrote a book on cryptology and describes a technique where messages are from a book, from a specific column within a book, and that's like the Beale treasury that we talked about. So encryption is a basic element of security, and encrypting data is when transmitting is an integral part of the security plan. And we know that we have a key, we have clear text, we have ciphertext, and we have an algorithm to do this. Thank you, and happy encrypting.